We left off last time, middle of section 12.1/12.2, and we're doing constructions. And the construction that we are on right now is the side angle side construction. And it occurs in the location where it's placed on purpose because last time, the last thing that we did is we talked about how to create an angle that was congruent to another angle, right? Okay, so read back through that really briefly. In fact, I'll flip back over to those directions that we kind of created for ourselves because we're going to need that as our very first step in this next construction. Okay, there it is. So we have an angle and we have a line, and we use the endpoint to create an arc on the angle that we started with. So the endpoint goes on the vertex and we create that arc. We put that endpoint on some other point on our current line that we're sort of, working as the surface on, and we created the similar arc to that. And then basically we measure the length of the arc in the original diagram, and then we use that length to create the same length of the arc in our new diagram. We connect the points and we have an arc, we have an angle using that arc that's the same length or same measure. So we're going to do that as we start this next picture. So grab your compass. If you don't already have it with you and out, you're going to need it. All right, so we're going to go to the very end of this presentation again, and we're going to write out the steps for creating congruent triangles using side, angle, side. So an angle trapped between two sides of information we were given. This is my side, angle, side construction. So I'm not going to write all the same steps out that I've done in the other ones because it's going to be exactly the same. So my first thing that I'm going to write down is I'm going to start with a triangle and a line. Okay, so that's something we need. So we start with and I know that when I'm giving you sort of verbal directions on how it makes it easiest to do, I told you that it would be helpful visually for you if you made the line look kind of parallel to one of the lines already. But there's absolutely nothing about that is mathematically necessary. It's just a visual thing for us. So that line really is an arbitrary line. It could be anywhere on the diagram, okay? All right, the second thing that we did is that we created a congruent angle, right? So we are going to just write that down because we already have steps for how to do that. You wrote it down last time. So we created a congruent angle. So now we have a triangle with one angle congruent to another angle that we've created. And then what did we do? Yeah, so we did a congruent side length, right? So we created a congruent, and I'm going to call it adjacent because it has to be adjacent to that angle, right? A congruent adjacent side. And we actually did that twice, right? So we created, we would create the other adjacent side. So now we have two side lengths marked. We have an angle measure we already found. What was our last step? What was it, Skylar? We connected them, right? We connected those two endpoints. So we connected the final side of our triangle. Any questions on that? All right, we have a few more definitions, and then we will encounter some more constructions. Here we go. Perpendicular bisector. A perpendicular bisector of a segment is a line that's perpendicular and it bisects it. Isn't that a fantastic definition? It means exactly what it says. So bisect means it cuts it in half, 2 equal pieces. Okay, so we actually talk about being able to bisect segments of lines. We can also bisect angles. We'll talk about angle bisectors at some point here. But what we're talking about here is being able to bisect a segment. And we're doing it in such a way that we're doing it perpendicularly, because we could bisect a segment at an angle, right? I mean, that would totally be a possibility as well. But that's not the description we have for this, this term. A point is the same distance from the 2 endpoints of a line segment if and only if the point is on the perpendicular bisector. So in terms of this picture, all it's saying is that if I have a point out here that's not on the perpendicular bisector, then there's no way that it's equal distance from A to B, as it is from A, from that point to A, as it is from that point to B. The only way that can happen is if the point is somewhere along the perpendicular bisector line. That's all it's talking about. And that leads right into something that we mentioned last time, and I said I think we're getting to it really, really soon about isosceles triangles. Do you remember talking about isosceles triangles briefly last time? Properties of isosceles triangle. The base angles are congruent. I told you that last time, right? Now you know I wasn't lying because it's in the notes, and if it's in the notes, it's got to be right. Right? Exactly. Exactly. Now, I mentioned just a second ago, too, this idea of angle bisector. So if we can bisect something and it just means cut it in half, we should be able to bisect, well, kind of whatever we want. So this one talks about now bisecting an angle. So it cuts the angle into 2 equal pieces. So the angle bisector is formed by the 2 congruent sides. And when that happens, it's actually perpendicular to the base. So if we have these 2 congruent sides, okay, it's isosceles, right? And we form the perpendicular, we form the angle bisector right here. It cuts the angle in half. Then it will also create a perpendicular down at the bottom. Those are related ideas. Okay, also related to the idea of perpendicular bisector is the term altitude. Altitude is often thought of as the height of a triangle, how tall it really is. So not all triangles are right triangles. They don't all stand up straight with one of their edges being perpendicular to the base, right? They don't all do that. But we have to still be able to measure the height of the triangle, and it's a distance argument. The altitude is the way we can do that. So this is the perpendicular segment from the vertex to the line opposite that vertex. A triangle, will have 3 altitudes, 1 for each vertex, and they all intersect in 1 point. So the one on the top is the one we usually think about. But if we take this top point and we drop the line down like this, it doesn't necessarily cut the triangle in half, right? There's a special feature when it does. But it can always be dropped down to do this. But if I can do it for one vertex to its opposite side, I could do it for any vertex to its opposite side. And the unique feature about that is that all of those 3 altitudes will all be equal. That's an important feature because it's the height of the triangle. I think I just said that wrong. They're not all equal. They're all intersected on a point. There's something else that's equal. There's something else, sorry. Getting ahead of myself in my notes. Yeah, they're definitely not all equal. But they do all intersect in the same point in the center. And that point in the center is going to have a special property that we're going to encounter here in a moment. All right, so take a look at this. Circumcircle. All right, so we can say that a circle is circumscribed around a triangle if every vertex of the triangle is on the circle. So if we could somehow take a triangle, and draw a circle around it so that it hits all the vertices, that's called the circles. It's called the circumcircle of the triangle. It circumscribes it. Okay? We could also say that the triangle has been inscribed inside. So inscribed is inside, circumscribed is on the outside. The point where any two perpendicular bisectors of the side of the triangle intersect is called the circumcenter, or the center of the circle. Yes. All right, so this point where these perpendicular bisectors intersect that we talked about over here has the ability to be the location of the center of the circle that we can draw around this thing and actually hit all those vertices. That's a pretty special feature. No other point in the circle will do that. It's just the circumcenter, that's the intersection of these altitudes, that will do that. Okay? So now we're going to draw one. You guys ready? No? Oh, come on now, Skylar. This is so much fun. All right, so first one we're going to do is we're going to do the perpendicular bisector one. And then we're going to do one that's going to be the circle circumscribed around the triangle. So we'll do the perpendicular bisector one. We'll write our steps like we've done before, and then we'll come back to the other one. So we're going to write out the steps for creating a perpendicular bisector. What did we have to do first? What did we start with? Yeah, we started with a line segment. Can we bisect a line? No. You got to have length, right? And a line doesn't have length. It's infinite. It goes infinitely in each direction. So we do need something that has a specified length. So it has to be a line segment. What did we do next? Yeah, we measured the length. And this is where, if you want to write this down, I'm just going to write measure the length. But if you want to write measure a little more than half the length, which just means you're going to write more than I am, you can. So measure the length of the line segment. Okay, we've got the length of the segment. Our compass is now measuring. What do we do next? Yeah, we drew an arc. And it needs to be drawn big, right? Like we draw, the arc itself isn't, well, yeah, the arc is big. We need to draw the arc so that it's basically almost a half of a circle around or more, right? So draw an arc. I'll say it this way, almost creating a circle. It was a really broad arc. And then what did we do? So we repeat. Step 3. Using the other endpoint. Then what? Yeah, we connected the two intersections of the two arcs. All good? Okay, I'm not going to flip back to the actual screen with this because I'm thinking when you guys look back at this video, you're probably going to be seasick with me flipping my screen so fast, so many times. So I'm going to pause there for that. The next one is that we're going to construct a circle circumscribed about a triangle. Okay? So let's go back and let's take a look at. All right, so what is the construction that we just did? What did we find or create? We created a circumcircle, or we circumscribed a triangle, however we describe that, right? So we circumscribed a triangle. We created it to be inside now of a circle. So we started with a triangle, right? That's all we started with. What did we do after we had our triangle?
We made arcs.
And why were we making those arcs? Yeah, so I'm going to, again, do kind of like what I did on that side angle side proof, or list of instructions. What we did is we did a perpendicular bisector of two sides of my triangle, all right? So we created the, not a, but the, there's only one, perpendicular bisector for two sides of the triangle. Okay, now we've got a diagram. I've got two perpendicular bisectors. What did I do then? Yeah, there was an intersection point. So we used the intersection of the two lines. And what else? Yeah, one vertex, right? Any vertex of the triangle. So, and one vertex of the triangle. In terms of the picture you're creating, what is that length represented? What is it? What is that length from this intersection point to the vertex? Not the altitude. It's a radius, because it's in relation to the circle that I was referencing, yeah. So this will be the radius of my circle. So we used this as the radius of the circle. And drew the circle. All right, we have two more slides, I think, in this section, so let's go back and catch those two. There's a timeout slide. That's where we are. Right here. All right, so this is not a construct, it's just a draw. Okay, so I'd like for you to draw a parallelogram and one of its diagonals. So start with that first. Okay, so draw yourself a reasonable looking, you know, conceptually you think, yeah, I think that's pretty good. It's pretty much a parallelogram. Draw yourself a parallelogram and one of the diagonals of the parallelogram. think I'm okay with that picture. And then we need the diagrams diagonal. And it could be either of the diagonals. It doesn't have to be the one that I drew. It could be the longer one. That'd be okay. It wouldn't hurt anything. It says to use the definition of what it means to be a parallelogram and the angle-side angle congruence property to show that the opposite sides of a parallelogram are congruent. So that is a fact. They really are congruent. We're going to try and justify it using these other facts that we've already established. Okay? Angle-side angle, what does that postulate or that congruence theorem tell us? What is it referencing?
If the if two angles and the side in between those angles are congruent on two triangles, then the triangles are congruent.
Excellent. Do you guys remember that one? We haven't proved a picture form of that. We haven't done a construction for that one. We have talked about that congruence theorem. So looking at this diagram, we do know the included side between them. It's that pink one that I just drew. That is the side that we're going to be referencing. So whatever our description is going to be referencing the angles that are surrounding that. So I'm going to do my best to get some colors so that I can talk about it in terms of colors. So let me do orange. So this angle and this angle is what they might be referencing. And then we'll do the other pair in a moment. So we have the included sides that are congruent. It's the pink one. Why in the world would those two angles be congruent? Ah, that pink line's a transversal to what? What are transversal? And when we say transversal, we're referencing parallel lines. You got it. Parallelograms are parallel lines. So if we reference these angles, it's the bottom and the top that we're actually talking about in this particular description. So I'll draw them in red. Oh my goodness, you're right on target. Yes, alternate interiors than we want. So this one and this one are parallel, at least they would be if I drew them well. And the pink line is actually creating a transversal. And those orange angles are alternate interior angles. But all of that hinges on the fact that we have parallel lines. And why do we have parallel lines? Because it's a parallelogram. Are you guys with me? So let's write down some of the language surrounding what we just said. Let me take those red lines away so I have some space. Okay. So because we have a parallelogram, and just for argument's sake, being able to write things out, I'm going to give my parallelogram some labels. So here's A, B, C, and D. Because we have a parallelogram, AB is parallel to CD. So angle, and again, I could use the letters for the angles, but I'm not going to. I'm going to use numbers because it's going to be easier to write up. I'm going to call these angles 1 and 2. You guys good with that? Okay, so angle 1 is congruent to angle 2. Why again? Yes, because they are alternate interior angles. And I'm going to abbreviate at this point. They're alternate interior angles. That's only one pair of angles and the included and a side that's adjacent to it. We need the other pair of angles as well, so let's actually mark that in a different color. How about my favorite color? Purple. So we'll mark these. These two are not using the top and the bottom sides of this parallelogram, are they? They're not. they're using the left and the right-hand sides of this parallelogram to make this claim. Because you have to see where they actually intersect. The pink line's still the transversal. I mean, that's definitely a true statement. Oops. But this line and this line, along with the pink line in the middle, are what's creating the angles that are created by the purple pieces. Those purple angles there. Okay? So when we're referencing this, it's not going to be because AB is parallel to CD. It's going to be because what? AD is parallel to BC. Okay, so we're going to write almost the same statement we already did, but it's going to be about different sides. So because AD is parallel to B, I said it right and I wrote it wrong. Let me write it again. AD is parallel to BC. Angle, and I'll call them 3 and 4. Angle 3 is congruent to angle 4 because they're alternate interior. Alternate interior angles. Now what? And the side, we know, right? And side, what side is it? We called it AC, the diagonal, right? Side AC is congruent to itself. I'm okay with you just leaving that, just so that you're aware. It's called the reflexive property, like your reflection in a mirror. Okay, that's the idea. This is a reflective property. Actually, yeah, I'm pretty sure that's correct. I haven't seen it in your book yet, but I'm pretty sure that that's the one that they'll use. So side AC is congruent to side AC. So we have triangle. What two triangles does this establish? Okay, DAC. And triangle BCA. Notice that just because the letters C and A are in both of them doesn't necessarily mean they have to be in the same location, right? It's not the same actually on this one. Okay, and this is by what? What proved that, or what? Angle, side, angle. Okay, since we have congruent triangles, what do you know about congruent triangles? Well, I mean, we just showed that they have two sides that are two angles that are the same and one side that's the same. That's enough to say that we know for sure that the whole triangle is congruent to the whole triangle. So what does that mean? Nope, not an isosceles triangle. We already know that. What does it mean for it to be congruent? What do you want to be congruent?
All the angles, all of the sides are congruent.
Yeah, that's what congruent triangles actually are, right? Is that they have pairs that are all congruent. I can pair everything up in a congruent fashion. So even though I didn't prove the other pieces, that we get them for free. So this means side AB is congruent to what side? DC. And side AD is congruent to what? BC. And this is where I had told you before that we were going to be able to write down a shortened form of something. We can say that this is true because corresponding parts of congruent triangles are congruent. But I don't know about you, but I don't want to write that many words out. Okay? And so there is an acronym where we did last time that corresponding parts of congruent triangles are congruent. CPCTC. If you just say corresponding parts, you're going to get the letters in there. It's going to be fine. But that's what it is. All right, so fun stuff. All right, I have a handout for you. We're going to talk through. We're going to move through it pretty quickly so that we can move on. But I want to go through this with you. These are for you to keep, yes. This is in lieu of me sitting here and just putting them all on the same slide. So you actually have a handout with them all on there. The handout chart that's in your book is not the best. And so that's your chart. These are quadrilaterals and their properties. Did I not give you enough? How did I count wrong? I was just the lines between 3 to throw for you up here. All right, so we've talked through one of these. We talked about the fact that a parallelogram has opposite sides that are parallel, and then they're also congruent. But we're just going to start at the top. A trapezoid is a quadrilateral with one or two parallel sides. We've already defined that before. You've got a picture as an image there. And then some of the related theorems are that consecutive angles between parallel sides are supplementary. So what does that mean in terms of the diagram? Well, in the terms of this diagram, if you take a look at the parallel sides, you can tell for sure that BC and AD are parallel in your picture, right? And those are the parallel sides. What this is saying then is that angle B and angle A are supplementary. And angle C and angle D are supplementary. It doesn't say anything about B and C. Those are clearly not supplementary, in fact, correct? Okay, but the angles that are between parallel sides are supplementary. All right, the second one, isosceles trapezoid. So we've used the word isosceles with triangle. Now we've got it with a trapezoid. A trapezoid that has two pair of congruent base angles. So angle A and angle D at the bottom are congruent. We call that an isosceles trapezoid. So by isosceles, it also means then that the two sides, AB and CD, are congruent. And we talked about how isosceles triangle does that too, right? The two sides and the two base angles are both congruent. What happens is we have a pair of opposite sides that are congruent. I mentioned that one. And then if the trapezoid has congruent diagonals, we also know that it's isosceles. So if BD, if that length we knew were equal to the length of AC, that would be a way to prove or to know for sure that we have isosceles trapezoid. Parallelogram, we actually ran into some of this one already. This is a quadrilateral in which both pairs of opposite sides are parallel. Opposite sides are congruent. That's what we just proved. You guys did it. I mean, you talked me through the whole thing. I didn't really have to tell you much. You knew what we were doing, right? We were creating these congruent triangles. Well, if the opposite sides are congruent, opposite angles are congruent as well. And that's, again, from the corresponding parts of congruent triangles. The diagonals also bisect each other. So here's my picture over here. Let me just pull it back up. So this was one diagonal. The diagonals, if they intersect, when they intersect, they actually bisect each other. In other words, on my picture right here, if I drew this one in, this length would be the same as this length, and so forth on the pink one as well. Those diagonals bisect each other. And a quadrilateral in which the diagonals bisect each other is a parallelogram. So you get sort of the reverse argument. If I knew that the diagonals bisected each other, I would then know I have a parallelogram. The next one is a rectangle. A rectangle has a lot of cool properties. This is a parallelogram with a right angle. All angles are right angles. We've talked through that. If you have a quadrilateral with all right angles, you definitely, by definition, have a rectangle. Its diagonals are actually congruent. They're the same length. And if you actually have a quadrilateral with congruent diagonals that also bisect each other, then you know you have a rectangle. So knowing one or the other of those things is not enough. You have to know both of them. A kite is a quadrilateral with two adjacent sides congruent and the other two sides also congruent. So the lines containing the diagonals are perpendicular to each other. A line containing one diagonal is a bisector of the other diagonal. And one diagonal bisects non-consecutive angles. So we've got a lot of issues of things bisecting each other in this one for kite. Rhombus. A rhombus is a parallelogram that's equilateral. Okay, parallelogram is equilateral. All of the parallelogram and kite properties hold because it is both a kite and a parallelogram. So you get all those properties above. You can also define a rhombus as a parallelogram with two adjacent sides congruent. You could use that as a definition instead of the definition we do use. The diagonals of a rhombus are perpendicular. So if we drew in the diagonals of AC and BD in that diagram, they would actually construct right angles. They would be perpendicular in the middle there. Not only that, but each diagonal bisects opposite angles. So it would cut the angles of your image in half as well. So like this image up here, you can see pretty clearly, I think, that my purple angles are bigger than my orange ones, right? Yeah. Well, that doesn't happen if you actually had a rhombus. They'd all be congruent when they crossed like that. And then the last one is a square. A square is simply an equilateral rectangle, or you can say that it's an equiangular rhombus. We've talked about that before as well. But all parallelogram, rectangle, and rhombus properties hold, because it actually is all of those things. So this is a fantastic thing to hang on to as you're taking a look at your homework, as you're referencing certain things. And we are now officially finished with section 12.1/12.2.